Encryption plays a key role in protecting confidentiality. If someone steals a hard drive or intercepts your data in transit, they can't read it if it's encrypted. That's why encryption is such a foundational security tool. As an IT security professional, you must be able to select cryptographic solutions that fit the security problem you're trying to solve. When planning encryption, think about all the different ways your data can be exposed. Data typically falls into one of these three states. Data at rest. This is data stored on a disk or other persistent media. Data in transit. These are data that are moving across a network. And then data in use. These are data that's being processed in RAM or CPU cache. Encrypting large volumes, gigabytes, or even terabytes is known as bulk encryption. We don't use asymmetric encryption like RSA or ECC for bulk data. Remember, it's too slow and it's resource heavy. Instead, we use symmetric encryption like AES, which is fast and efficient. But symmetric encryption has one big challenge: key distribution. The more people who have access to the key, the less secure it is. To solve this, we combine symmetric and asymmetric methods. Here's how a typical hybrid encryption system works. The user generates an asymmetric key pair, RSA or ECC. Their private key is encrypted and locked behind their login. This private key is the key encryption key, KEK. Alright? The system then creates a symmetric key, which is like an AES 256 or AES 512. This is called the data encryption key, DEK. The DEK is used to encrypt the data. Then the DEK itself is encrypted with the public key from the KEK. To access the data, the user must authenticate to decrypt the DEK using their private key, which then decrypts the actual data. Alright, you got all that? As long as it makes sense, you can move on. If not, rewind. Now let's talk about data at rest. This includes everything from hard drive to SSD and USB sticks. You can apply encryption at various levels. Lower levels like full disk encryption, these are easier to manage. Higher levels like file or database encryption offer more granular control. Full disk encryption encrypts the entire content of a drive, including metadata and free space. This is ideal for preventing access in case of physical theft. A stolen laptop with FDE is useless to the thief unless they can unlock the disk. Some drives come with built-in encryption. These are called self-encrypting drives, SEDs. These could be hard disk drive, HDD, or solid state drive, SDD, or even USB drives. The encryption happens in the drive's firmware using a built-in crypto processor. That way, the key never touches the operating system directly. You can also encrypt individual partitions on a disk. For example, a disk may have boot, system, and data partition. The boot and system partition, which hold operating system files, can stay unencrypted. The data partition, where the sensitive information lives, gets encrypted with its own key. Some tools even let you apply different keys to different partitions, offering more controls over who gets access to what. Alright, that's all for now. Here's a recap of what we learned. Cryptographic solutions match tools to specific security goals. Encryption ensures confidentiality across data at rest, in transit, and in use. Symmetric encryption is fast for bulk data, but we use asymmetric encryption to safely distribute keys. And lastly, full disk encryption protects against theft. Self-encrypting drives and partition encryption adds flexibility. See you on the next one.